So good morning, everyone. This is Wednesday. It's 10:02 a.m. So it's Enjoy Science time. So my big pleasure to welcome all of you, large family of MD Anderson from inside the institution from all over the world. And of course to tell thank you and welcome Dr. Kulen Taniguchi, who is our speaker from today. Certainly this is a great series of talks, and I have to thank mostly to Liz Kent, to Alison Gar, to Laura Adame, because without their work behind the scene, nothing can be done. This is hosted by the Chief Scientific Office by Dr. Giulio Draet. I host it happily with my friend and colleague Alessandra Ferraioli. And with this said, let's run the show. So it's my pleasure to say hello to Kulen. I know him for a long time, and many of you from inside and outside MD Anderson, you know Kulen, not only because he's very smart and he's a wonderful clinician scientist, but because he's very collaborative. And all the time when we discuss with Kulen, you see a big smile, and he's all the time ready to work and give advices. You know very well he's an associate professor. He has a wonderful background. He started somewhere named the Occidental College in California, and in fact, his life started scientifically in the true Occident, in Oxford, in UK. Then he moved to Harvard, then he moved also to Stanford. So all these are wonderful backgrounds. And in fact, in MD Anderson, he set up a very strong group in radiation oncology. He is publishing extraordinary research, very collaborative, and a lot of clinical translation. And with this said, let's Kulen to run the show. Thank you, Kulen, for being here, and good luck with your talk. We are all very curious about your new data.
Thank you, George. And thank you for the invitation today. I'm very, very excited to speak to everyone here. Thank you for spending some time midweek to just talk about some science. And what I want to talk to you about is reducing radiation toxicity. And it might seem a little strange coming from a radiation oncologist that my job is to use therapeutic radiation to kill tumors wherever they may lurk in the body. But, you know, as someone who knows this modality well, I know all the things it can do, and I know some of the side effects that it can have. And that's what has, the patient experience has driven me from the beginning to all my research and translational work. So I'm going to be highlighting work from our lab, and how that's blended into the clinic with clinical trials. All this stuff here has really not been kind of a conventional approach. It's been really, I think we're still gaining acceptance across scientific fields, but I think you'll see that if you kind of stick to your guns and listen to the patients, that good things can happen. I have some disclosures here, mainly from working with some radiation machine companies. And I'll actually go over almost everything here as part of the science that we'll talk about today. So here's, you know, we talk about immunotherapy as one of the pillars of cancer therapy. And actually, this is from Dr. Allison's Nobel Prize announcement here, where immune checkpoint is the fourth pillar of cancer treatment. And I think that if you talk to people on the street, they'll say, oh yeah, surgery, you get chemotherapy and immunotherapy. But probably even amongst doctors, they might not highlight radiotherapy as a pillar of cancer therapy. It's always been there as long as we've had multimodality therapy, and it always will be. It has very specific roles, and which can't be easily replaced. And so we'll go over that in a little bit. And so as cancer doctors, when we're have this very difficult a problem of killing a tumor that is partly made up of a patient's own normal cells, it's always a challenge that you want to kill the tumor without hurting the patient or irreversibly hurting them so that they can't live the life they want to live. So ideally, so for some of you who like to think in mathematical curves, this is kind of the calculus that all oncologists make before prescribing any kind of treatment, they think about the normal tissue damage here in red, so how will it hurt the patient potentially, and the therapeutic gain here in green, in tumor control. And so in the ideal situation, you'll have a high amount of tumor control with very little normal tissue damage. So, and unfortunately, there are very few instances where we have curves that are separated by this much. In reality, we have something more like this, where the tumor control, every bit of tumor control comes with a proportional amount of toxicity. And the higher you climb the curve, the more you push the patient to the brink of really untoward outcomes that you want to avoid. So how can we do that with radiation? So I know that this is a sophisticated audience, but not everyone might be familiar with radiation therapy. And so in explaining this to my students, I actually have a very talented student named Jay Fan, a Rice University graduate, D1 football player, and someone with a videography skills. So he put together this 1-minute video to use as an analogy about extermination and how that fits into the oncology landscape. So I'm going to play this for you, and hopefully you enjoy it. It's about a minute long. Radiation. I hope you enjoyed that. That is essentially what radiation is. No, we don't. I don't want to extend any misconceptions about radiation. We don't actually burn things. It's you'll often hear things about radiation burning folks, but it's actually invisible. You don't feel it. You don't become radioactive. It's the therapeutic X-rays that we use to take CTs and chest X-rays, but we turn up the intensity and aim it only at the areas with cancer. So you don't feel it. You don't glow in the dark or anything like that. But as you can see that there are very different roles for it. So it's kind of a mix between surgery and chemotherapy in its ultimate role here. And how I think about this is in pancreatic cancer. This is a very deadly disease, as many of you know, that it kills almost every patient that gets diagnosed with it. And its incidence is on the rise. And so there's some folks at PanCan who actually did this analysis. That's a major patient advocacy group. And what they figured out was that with the rising incidence of pancreatic cancer and the overall survival rate, about 10%, that it will account for the second most number of cancer deaths by 2030, and it's still on pace to do that. And the main problem here is that there's a very narrow window of people who can be cured with pancreatic cancer. So most people present with metastatic disease where it's spread around the body. Very few people, only about 10 or 15%, have a tumor that can be cut out. And this is actually what the tumor would look like, and this is the nearby duodenum. So it's a little bit real picture here, but this is a specimen. This is what you want to see when the tumor is cut out. And the rest of the patients, about a third here, have a tumor that's wrapped around blood vessels and can't be cut out. So In this case here, it's really not clear what to do. Ideally, you'd like to get these patients to surgery where they have a chance to be cured. But how do you get them there with chemotherapy, with radiation, and what if surgery is not on the table? So that's kind of where we're starting. And that we know, and if you accept my premise here, that pancreatic cancer can only be cured with surgery. That's all that we know. And even surgery is no guarantee, but that buys your ticket to the lottery if you can get surgery for pancreatic cancer. Most patients can't have an operation because we don't have any early detection systems. And so patients are found incidentally, or if they have symptoms of it, such as jaundice or abdominal pain, often that means the cancer is already advanced and often can't be removed surgically. So what do you do with this problem with a bad cancer that needs to have surgery to be to have a chance for cure, but most patients can't have an operation? So we took a cue from lung cancer. So lung cancer is one of the most common cancers linked to smoking. And there was this cohort of patients with early stage lung cancer. So they had basically a tumor in their lung, one single tumor. And, often this went with patients who were smokers and had other medical comorbidities to the point where they couldn't have surgery. Because surgery there was also considered the standard of care. And what they found was that in these patients, that if you did nothing to them, that the cancer would kill them in 5 years, about 90% of the time before emphysema, heart disease, or kidney disease would. So it had an imperative to do something. And what do you do in these medically inoperable stage 1 lung patients? So through clinical trials and through innovation of physics and radiation, that this approach of stereotactic body radiotherapy, where we'd basically think like a surgeon and use radiation to destroy a tumor in the body using the most advanced imaging that we have. And with that, these patients who would be 90% of whom would be dead from cancer in 5 years, now we can cure almost half of them. So it's a very, very promising modality. This is for lung cancer. So one of the reasons we can do this with lung cancer is, it's somewhat easier to see a tumor in the lungs. That it's a spongy tissue, and a solid tumor is something we can really focus on and target. Your lungs have a lot of redundant tissue that if you cut out one part of your lung, that there's still other parts that can exchange oxygen. So those are some things that allow high dose radiation in the lung. But in the pancreas, it's challenging, to say the least. So this is a Netter's drawing diagram of the pancreas and the nearby anatomy. So normally the liver would be over this, and it's retracted here. And here's the tumor in the pancreatic head. So this is the most common place that it would show up. And we know that this kind of tumor takes a lot of radiation to kill it. It takes a lot of chemo, it takes a lot of radiation. It's a very, very tough cancer to kill. And we have this number here that you need to give the equivalent of somewhere about 70-something gray to kill it, which is a lot of radiation. We know that because the nearby bowel, this piece of in small intestine called the duodenum, it's the first part of the small intestine right after the stomach. And we know that if you give it much more than 50 gray, then you start to have some side effects, including ulcers and basically breakdown of the intestinal tissue, because it's such a rapidly dividing set of tissues. So you have this problem where you have a tumor that is very resistant to treatment right next to tissues that are very sensitive to the same treatment you're giving. So that creates quite a problem. On top of that, this high value real estate area, again, your liver's over this, the stomach is right here. That's what was cut away here. And it's over these major blood vessels, the major branches of the abdominal aorta. There's sensitive nerves and lymph nodes there. So there's a lot of high value real estate in a very small area. So in the past, we've used fancy physics to overcome this problem. So there's a lot of alphabets here, something called IMRT, intensity modulated radiotherapy. And basically, instead of using a few beams, we use multiple beams from multiple angles to hit the tumor, but not things like the kidneys or liver. And then we can go even fancier by using protons. So we actually take hydrogen atoms, accelerate them to the speed of light, and create a beam that focuses right on the tumor. It has these special characteristics where it can basically deposit its energy into the tumor. But because the duodenum and the pancreatic tumors are so close together, even with the most advanced physics, it's almost impossible to not hit the duodenum. They are connected. They're literally connected anatomically. For any of the medical students in the audience, you know that there's a common duct that connects them. It's part of digestion. So it's a very, very difficult problem to overcome. So how do we overcome this problem? That's what we've been thinking about. And so if you have a duodenum that can only take 50 gray, what if you could just make it take more radiation, make it a bit stronger, so that you could actually give the dose that you need to get rid of the tumor? So that's a very simple premise. And if there was an easy answer, it would have happened a long time ago. But that was the basis of kind of the research that I wanted to do. So again, here's where we're at with pancreatic cancer. And essentially by protecting the normal tissue, that we can get this separation of the curves that we want. So it's pretty much the same thinking that almost all oncologists have in terms of differences between killing tumors and normal tissue damage, but really here focusing on preserving the function of the patient's normal organs and tissues. That was my question. So how do you do that without also protecting the tumor? So I think that's something you have to do. You can't just protect everything and then protect the tumor. Otherwise, you have no selective advantage there. So I'm going to tell you a couple stories here today. It's kind of a 10,000 foot overview of them, and just to get you an idea of what we're thinking of. So our lab is focused on hypoxia and how to basically use the biology of low oxygen to kill tumors better. So we have tools that use that as a way to protect the normal tissues, but I'm a bit agnostic when it comes to this problem because there are many different ways that we can do it. So I'm going to show you a way to basically trick the normal tissues into thinking they're hypoxic and unleashing a superpower of the intestine. Taking an old drug that was developed by the military to protect soldiers on the front line from nuclear fallout as another protective drug, and also a really cool story from a graduate student about fasting. So that through your diet that you can actually reduce radiation injury. And then a drug that we pushed through clinical trials, and I'll show you the results of them that were recently completed, that to take this approach to the clinic and how it has the potential to make a difference in this disease. So first we'll talk about hypoxia mimicry. So that's kind of a mouthful there. And this is, for those of you who do not know the HIF pathway, this is, a lot to take in. So really for the aficionados here, I'm going to do it the aficionado way, and then we'll do it the more general way. Okay, so I'm talking about a set of proteins called the Eglin proteins, and they are prolyl hydroxylases. So they sense oxygen in the body. And so a Nobel Prize was given for this in 2018, how the body senses it. So this enzyme actually takes oxygen straight from your blood and puts it on the sensor protein called HIF. And HIF, actually, when you have normal oxygen levels, I should say here, it gets this, there's this beacon here of a hydroxyl group that is actually taken straight from the air. And when it's hydroxylated, it gets destroyed. So your body is making this HIF protein, hypoxia-inducible factor. It's getting hydroxylated and destroyed 24 hours a day, 7 days a week, all the time, as a way to sense whether you have enough oxygen. And the reason for this is quite simple, that if you actually ever are in a situation where you're in lower oxygen, your body needs to respond fairly quickly. And in that way, then if HIF is around and stabilized, it goes to the nucleus and creates a very, very powerful program to protect the cell from immediate death. So it's actually we think about it in cancer. Often it's something you'll study that maybe tumors have usurped, has co-opted to survive and grow better. But actually, one of the reasons that this has evolved is to actually protect cells and tissues from low oxygen so that you don't die instantly when oxygen levels are running low, and also to help you adapt to potential low oxygen in the future. So what this pathway is doing, so if you were to inhibit these eggland proteins, this oxygen sensor, you could trick the tissue into thinking that it's in low oxygen when it's actually not. Okay, so then you get the protective benefits of this hypoxia pathway of HIF without actually being in low oxygen. So that's a key point here. And so I was trying to think of a better way to explain this for those who don't know. And so this might be over the head of some folks, but I have two daughters. They're 9 and 5, and during the lockdown, we watched a lot of Netflix, like a lot of other people. And so we went through the Avatar: The Last Airbender series. So for those of you who do not know what this series is, one, it's kind of an old retro cartoon, really awesome cartoon actually. And the main character is this guy named Aang. Okay, he's this little boy who's the chosen one. He's got the superpowers to save the world. And for various reasons, the problem is he does not know how to unlock these powers to save the world, and can only realizes he has them when he or his friends are in grave danger. Okay, so he's this boy. He's kind of a silly boy, and but when he's in danger, he has this basically, godlike superpower that he can protect his friends and save the world. But it takes him a while to figure out how to do that. So this is my analogy of what HIF is. So we often think of HIF as something, we think of this part of HIF, that this is what it does, but what if you could modulate that just when you need it? So if we inhibit these oxygen sensors to trick the cell that it's in danger when it's not, we can use this superpower to resist radiation toxicity in the intestine. So that's inspired by Netflix with my kids. So hopefully that's just another way of why we're doing this. So I actually use this in my postdoc. We could protect mice from lethal radiation. So we showed that this could work. That's what this slide is. We don't need to focus any more on this. But how did we translate this to the clinic? Because I'm not going to try to hurt my patients with radiation. We just want to avoid side effects of it. So it turns out that these eggland inhibitors, also known as prolyl hydroxylase inhibitors, were being developed by several companies. And one was developed by this company called Fibrogen, which we were able to get this drug to test in a preclinical setting. And the long story short here is you want to show that at baseline without the drug, that these powerful oxygen sensing pathways are not activated. So HIF1 and HIF2 are not expressed. These are Western blots here. And then when you give the drug, it expresses it a lot. So this is our intestines in mice that we tested the drug on. And this is Tara Fujimoto, who's my lab manager, and was basically, we kind of cooked up this project together, and this is a testament to her hard work, a lot of this project here. We also made sure that this didn't protect tumors. So these pancreatic tumors are very, very hypoxic on their own. That's a whole nother talk, but just you can see here, if you're looking at HIF levels, that they're very high at baseline. And then if you give FG4592, it doesn't make it go much higher. The volume's already at 10, it doesn't go to 11. And that's basically what we saw. So it turned up HIF in the intestines to make them think that they were in low oxygen. And so what we did was we gave mice radiation that would be enough to destroy the tumor, but would be too toxic otherwise. And here we gave 75 gray in 15 fractions with just a salt control, saline control. And the mice all died fairly quickly after the completion of radiation. However, if you gave this drug, they all lived beyond 30 days. So it unleashed a superpower in the intestines. And what's great is this is a drug that was already developed for other indications. Really, it was developed as an anemia drug. So what was great is we took this drug, used it in a similar fashion, and so one of the things that we've done in our mouse models is that we have these mice that unfortunately for them, they develop pancreatic cancer on a regular basis. And so what we do is we develop them and diagnose them with pancreatic cancer. So we have a teeny tiny ultrasound that Tara does on the mice, and when she finds a tumor, we enroll them in a trial. So these mice are born, they get cancer, they're enrolled in a trial, and we try to figure out what's the best way to do this. So this is kind of like, again, a full preclinical trial. The mice all have the same genetic background, but they get randomized to, in this particular trial, the vehicle or a drug alone, and radiation with or without a radioprotective drug. And then we do survival analysis, and we have a pathologist take a look at what the cause of death might be. And so we had a lot of help here from Dr. Lauren Colbert, who was a resident at the time and is now on the faculty here in the gynecology oncology department in Red Onc, doing exceptional work in microbiome. But her work here was on clinical trial design. So we had a clinical trial design specialist help us with some of the statistics and design, and we can see here that these curves are all kind of they look kind of close together, but we enrolled 70 mice to get the statistics right. This is a very bad tumor, as any of you who work with KPC know. But so if you don't give any radiation, these mice that have essentially a mouse model of locally advanced pancreatic cancer, they die fairly quickly here in the black dotted line. If you give them FG, actually, interestingly enough, they survive longer, and we still haven't figured out why that is. If you give them radiation, however, they always do better with radiation. So and we'll show you why. And if you give radiation with a protector, they do even better than that. So it's the best survival curve. And that's statistically significant. And the reason is this. So we have a pathologist here, a veterinary pathologist who looks at this and can basically determine, after looking at the mice when they pass away, whether they've had tumor progression, whether they died from the tumor growing and blocking an intestine, or from the tumor spreading around their body. In this case, what we see is if you give this high dose radiation and no protection, the mice end up dying from our own treatment. That's 56% of the time there's a bleed and they end up dying. But with protection, there is never a bleed, and we actually stop local progression. The mice end up still getting metastases, but that's because we don't give chemotherapy, we don't give a systemic drug. And we're doing treatments now with systemic drug, and we think that's going to be a key thing. Basically, it'll be just like what we give patients. So in this one, we're kind of blazing through this, but I want to get to the other stories here. So in this KPC model, it's a mouse model where they get locally advanced pancreatic cancer. The tumor grows and causes an obstructive death. And if you give radiation, you shrink that tumor, but if you give too much like we did, then they die from bleeding. However, if you give, or metastases, however, if you give radiation with a protector, we stop the bleeding, but they still have disease that spreads throughout their body. And in this case, if you give chemotherapy, in data we're working on now, that reduces it and they live even longer. So those are the next steps. And that's actually how we treat patients. They get chemotherapy, and then if their disease has responded, we give them radiation. And I'll show you that at the end in the clinical trial. Okay. So I want to touch briefly on these two other smaller areas that we have working to translate to the clinic, but are definitely we're in the preclinical stage here. And I teased this in the beginning that this was something developed by the military, and indeed it was. It was developed by the Walter Reed Institute of Research, and it was basically in the specter of potentially nuclear war, and realizing that our soldiers on the front lines needed something to protect them from radiation injuries. And so they developed a drug called WR for Walter Reed 2721, and it's also known as amifostine. So some of you know this. But this is probably the most well-known and actually best functioning radioprotective drug. It's actually FDA approved to reduce injury to the salivary glands and head and neck radiation. Was actually taken to space by astronauts in case of solar flares. And we're actually working with NASA to develop the next generation of radioprotectors. But this drug has a known history and it works. So for those of you who recognize molecules in chemistry, I think you might find this interesting. So one of the first projects I came here to work on, I worked with Kathy Mason, who is now retired. Professor of radiobiology, was a great mentor to me when we got started here. And Jim Tuer, who's a professor of chemistry at Rice. And so they were interested in translating some of the things that they found to the clinic as well. And so they basically tested tens of thousands of compounds that Jim had synthesized, and nothing performed better than amifostine. So even then, 40, 50 years later, amifostine was still the winner. And how this works is it's this very simple looking drug with a phosphorothioate bond. So it looks like a phosphate and bound to sulfur. And basically natural enzymes that we have in the body called alkaline phosphatases, which are in your bones and actually in your digestive system, that cleave this phosphate and produce this thiol, which scavenges free radicals that are produced during radiation. So that is the basis of why this is a protector, because tumors don't tend to express alkaline phosphatase, but they're expressed quite highly in the vasculature, in intestines and bones and many normal tissues. So the idea here, actually, for some of you who do some molecular cloning, this was something I thought about, and going back to the basics, that there's the duodenum actually expresses a lot of alkaline phosphatase. It's actually an enzyme that we use to digest phosphate groups, because when you eat meat or actually anything that has ATP, you need to break down the phosphate groups. And it gets activated in the duodenum by changing the pH. We know your stomach is acidic. It goes into the duodenum here in the intestine, your pH goes up, it becomes basic. And so that is a requirement to basically let your body know that the food has moved on to a different part to neutralize the acid here. And so in the duodenum, you have a lot of this alkaline phosphatase, primarily for digestion. So the simple thought that we had was, this drug, amifostine 2721, if we want to have a drug that's right in the duodenum to protect the duodenum from radiation injury, could we essentially apply it topically, give this drug, and where it won't get activated in the stomach, but have it show up in the duodenum and get cleaved by alkaline phosphatase to its active form. This other one called WR1065. So I want you to remember 1065 is the active drug of this. So it's, again, the idea is to basically use the natural digestive enzymes in our body to activate a protective drug only in the area that we need it at the time that we need it. So there's a lot of data here, and I bring up this slide to say that we did some of the pilot experiments with Kathy and Jessica Molkentime, who was an amazing research technician, is now moved with her husband to Pittsburgh, and they took a great job there and showed that this premise worked, that giving this drug orally is a protective drug, because normally this is given by injection, and it protects the intestines and really nothing else. And it doesn't make the mice sick. If you check their body weight and you measure their food consumption, if anything, they eat more. So that was quite heartening. So the key thing here was to actually convince people that we're activating this only in the intestine. That's where I realized I was kind of out of my element. So I want to give a shout out to Phil Lorenzi at the Metabolomics Core. Again, this is where collaboration comes into key. We have great ideas from students. We have collaborators who have helped bring these ideas forward. So we basically, with Phil, were able to work with his team and develop a custom mass spec based assay to measure the active metabolite in tissues. And so based on that, we're able to show that if you give this drug orally, that it gets activated only in the intestines and nowhere else. If you give it systemically, if you inject it into the belly and it gets absorbed into the blood, it goes everywhere at about the same dose. So that's what this slide's a little busy, but that's essentially what it shows. And if you do the same thing to mice with tumors, it goes into the intestines, but not into tumors. But if you give it by an injection, it goes everywhere pretty much the same. So this right side of the graph is not what you want. This left side here, where it's many fold higher in the intestines, is what you want. So if you look at it this way, giving it orally, it gets 10 to 30 fold enriched in the intestines compared to tumors, whereas it's really about the same in all tissues if you give it in the blood. So that is something that, was very exciting for us. And when we gave these KPC animals, radiation, it protected them from very high dose radiation. So we gave them up to 12.5 gray times 5, which sounds less than before, but it's actually the equivalent of giving about 113 gray. And so without this protection, the mice died from bleeding. And if we give the mice with tumors this high dose radiation, we're able to improve their survival compared to vehicle controls. So that was something that was very, very heartening, and it's something that we are actually, company has actually, we patented this, so that's another part here. MD Anderson has a great intellectual property team here. They helped me get this patented. I had no idea how to do that. They helped me with that and actually got licensed, and so maybe we'll bring this to a clinical trial in the future. So again, this is a team effort. A lot of the stuff I had no idea how to do. We had the idea from patients, but it was really working with other people here that we were able to move the science forward towards the patients to help them. This last part here of the preclinical is a story about fasting and radiation protection. So it is just something because we fasting and intermittent fasting and diets are all the rage. And some of you who are observing Lent are probably thinking about this as well. So what has been shown is fasting is this really interesting property that it reduces oxidative stress. And in the lower organisms, such as C. elegans and E. coli yeast, it actually improves lifespan and reduces oxidative stress. So it's just something that's been seen to be conserved across basically all species, except for humans. So that's not, actually humans, caloric restriction has improved lifespan too, but this oxidative stress thing is tricky because we don't know how long it is. So what about in mice? So I will say that this is another area of collaboration where these studies have been out there, but it was when I first got here to MD Anderson and I saw a talk with Dr. Helen Pinnacle Worms, and it was just the most fascinating talk here that she showed that in their lab when they fasted mice, that you could give them a lethal dose of chemotherapy, this drug called etoposide. It's quite common chemotherapy, and they live if they fast, but if you just let them eat like normal, they all die pretty quickly. And if you look at their intestines, basically the chemotherapy just shreds it up here. But when they're fasted, it's as if they never had chemotherapy at all. And this type of etoposide, it does damage similar to radiation. So we struck up a conversation after one of our seminar just like this, and we decided to collaborate on this. And we had a very an amazing graduate student, MD PhD student, Marimar de la Cruz Bonilla, who is now an MD PhD. So Dr. de la Cruz Bonilla, who's actually matched at Texas Children's in pediatrics on the physician scientist pathway. Great success story, but she stuck to her guns on this one, and she believed in the story too that that one way or the other we could understand if fasting could also protect against radiation injury. So kind of a similar setup to the chemotherapy experiments. The mice were fed or fasted for 24 hours, then returned to the cage, given radiation, then returned to the cage and allowed to eat. So we give them radiation to their belly, and lo and behold, if you basically phenocopy this, the chemotherapy study, where if they were fasted, they lived. This is a survival curve here, and if they just allowed to eat whatever they wanted, they were all dead. The mice just stopped eating food, and so it was just this fascinating phenomenon that they lost a little bit of weight and they gained it all back. So this prolonged fast unleashed the superpower, much like how we tricked we tricked the cells to thinking that they're on low oxygen, but also by prolonged fast, it did the same thing too. And what what Marimar did that was really cool was she really took a deep dive into some of the mechanism to understand which cells were being affected. So we first looked at using this classic crypt assay where after radiation, whether they were fed or fasted, we counted the regenerating stem cells in the crypt, and you could actually identify them here in H&E, and there were more in the fasted state, and we quantified that. Sorry, I went backwards. We quantified that, and there were statistically more if you fast before lethal radiation. And then she actually did lineage tracing, and this is a pretty cool experiment here. Very, very time consuming for those of you who know this. So basically the stem cells of the intestinal crypt are fairly well known. You have these LGR5 stem cells, which are thought to be kind of the master stem cell. And there's also this quiescent one, BMI1, which is classically thought to be responsive to radiation. So there's a question about which one was more dominant, if it protected both. And so they did this great experiment where crossed these mice with a reporter of XGAL. So basically what happens is, so I want to take a step back here. So this XGAL reporter turns the cells blue. So basically if you destroy the stem cells and one particular stem cell is protected, then you'll see more blue in that lineage tracing line, and you won't see it if it's another line. So here's what it looks like. So you can actually take the intestines and look at it on whole mount. So it's a little weird to look at this one down here with the little blue streaks on it, but these are actually intestinal villi of the mice. So what it is if you don't already know this, that the villi are finger-like projections that stick up from they're microscopic, and they help to increase absorption, kind of like a shag carpet. That's kind of what it, you can't see it until you look at it with a microscope, but this is essentially what this does to increase the area of contact with food and digestion and absorption. And so what you can do is you first look at it this way, but then you cut off the villi and look down into the crypt where the stem cells are, and you can actually count each crypt this way. So this is a really, really time-intensive technique. And so basically when she looked at LGR5 cells, fed versus fasted, you can see that there are more blue crypts here in the fasted state. And when she quantified that was, and after radiation, that there were more. But the BMI1, which is, again, a classically kind of radiation stem cell, there was some protection with fasting, but it wasn't significant. So we argued that, this is primarily an LGR5 phenomenon, although for the aficionados in the audience, we can't know for sure if there's some interconversion between BMI1 and LGR5, but this is a really cool experiment, very, very time intensive. And so, and she also showed that fasting does not change the way that KPC the pancreatic tumors respond to radiation, doesn't protect the tumors. And by doing this fasting, we could give a big dose of radiation, protect the mice. And so in this red curve here, if you fast the mice and give them radiation, many of them live quite a long time. So this was quite an interesting phenomenon. I think the hard part here, I think, for if anyone's wondering, it's hard to ask patients with pancreatic cancer who already have issues eating to fast for that long. It's hard for them. It's hard for us to ask them to do that, but fasting mimetics are being worked on. So to understand what the exact biology of fasting that's being enabled here is the key to translation. So we're approaching some of the time here, but I just want to highlight that this is something that we can translate. So based on the work that I've shown you in the preclinical setting, that we had collaborated with a company that had a different kind of radioprotector. And so I'm going to go over it here, but we actually presented this data in the fall last year. It was an oral late-breaking abstract. So this was a clinical trial that we worked on for several years. It was investigator-initiated. So this is something that we helped design, collaborate with the company, and we got this off the ground. So it was a very unique design, high risk, high reward. And this company uses something called a dismutase mimetic. So I will say that it's a mouthful, and I'm going to try to simplify it here, but essentially radiation causes the formation of free radicals, in particular these free radicals called superoxides. So the more radiation you give, the more superoxide you form. And they're actually formed from oxygen and water that's just in every cell. So when you do that, so normally you have these enzymes called superoxide dismutases that take these superoxides, which will really hurt your DNA and other parts of your cell, and turns it into hydrogen peroxide. Now, some of you might be saying, well, that doesn't sound much better, but your body has evolved to actually respond to hydrogen peroxide. So in the normal cell, you have these peroxidases that convert hydrogen peroxide to water and oxygen. So it just converts it right back to water and oxygen, which is obviously benign and something you want. And for reasons we don't completely understand, in many cancer cells, hydrogen peroxide ends up being much more toxic than in normal cells, that they don't express peroxidases like normal cells do. And so this hydrogen peroxide can build up and cause oxidative stress and selectively kill cancer cells. So it has basically two things. It protects normal cells from superoxide damage, and potentially by converting everything to hydrogen peroxide, it can sensitize cancer cells to radiation injury. So that was the thinking here. Actually, the first trial that was done was a successful trial in head and neck. So they showed a 40% improvement in mucositis. So it was the first time that's ever been shown. And so, after this, they were looking for other indications, and, they talked to us about pancreatic SBRT, which seems very, very different, and it is. But the reason you want to do that is that I mentioned that superoxide is produced in a dose-dependent fashion. So here's actually the preclinical data that justified this. I think this has just been accepted at Science Translational Medicine. Essentially here, so if you look at, these are PANC1 xenografts here, and that if you give the drug GC4419, it does nothing. If you give a 12 gray of radiation, it stops the growth and it comes back. But you combine the two at this high dose, 12 gray, you produce this superoxide, which gets converted to hydrogen peroxide, and it has long-lasting effects on the tumor. And so to really show that it's the hydrogen peroxide, what you can do is overexpress catalase, which is a natural enzyme that breaks down hydrogen peroxide. So again, you have this vehicle, and the drug really doesn't do anything. You give radiation, it slows it down. And then you give the drug with radiation, and you get complete tumor control. Now, the cool thing, the kicker here, is if you give catalase, you can turn it on in a doxycycline-dependent fashion. You eliminate this tumor control. So the formation of hydrogen peroxide is very essential to this mechanism. So that's what we think is going on here. So again, this is a dose-dependent fashion, so it makes more sense if you're going to give high-dose radiation over a short period like SBRT. So I just want to show the essence of this trial. We took patients who couldn't go to surgery, got chemotherapy, no metastases, and everyone got radiation, and they were randomized to get placebo or this dismutase mimetic. Okay, so a busy slide, but that's essentially what it was. And the goal of the trial was to find what dose of radiation was optimal for each arm. We won't talk about that today, but I'll show you the results from just a tumor control standpoint. Each arm was fairly well balanced. What was pretty amazing here was that 54% of patients on the drug arm responded, and you can see that the overall survival hazard ratios were 0.3, and it was there's a p-value of 0.046, but again, this is an early time point, so I'm not going to hang my hat on that too much, but certainly the hazard ratios are favorable for survival and progression-free survival. And these are the Kaplan-Meier curves for those of you who like to think of it this way. So progression-free survival, this is any progression at all. It was in favor of avazapazim, though not statistically significant, and overall survival, again, in favor of this dismutase mimetic with high-dose radiation, p-value less than 0.05, but again, early analysis, early interim analysis. So I don't think that we can scream from the rooftops just yet, but it's certainly promising. So one thing that's interesting here is, you see these kind of waterfall plots, and for those of you who don't not know, it's basically you take the response of the tumor, how much it shrinks or grows. So if it goes up, the tumor's grown. If it goes down, the tumor's shrunken, and each line is a different patient. So it gives you kind of an overview of the entire population. So you'll see this with many new drugs, but you often don't see this with radiation, and particularly in pancreatic cancer, where it's kind of thought that the tumors don't ever respond very much. But as you can see here, the tumors that got this high dose radiation with this drug, many of them had a shrinking of the tumor, and compared to placebo. And what you see here, this R0, it means some of them actually were able to go to surgery. We were able to take people that couldn't go to surgery. They were able to then go to surgery, and R0 means they got all the tumor out. There was one R1 resection that was in the placebo group. And actually there was one pathologic complete response. So not only when they took the tumor out, it looked like basically it was completely dead. So, and that was in the drug arm. So that was a really interesting response. Toxicity, basically there are no severe toxicity at all, no grade 4 or grade 5, and there are only 2 grade 3 events per arm. So the toxicity, at least in the acute setting, wasn't too different with it, but there was really a difference in tumor control. So basically that's how we translated it. So based on consistent preclinical messaging about protecting the gut and having this difference in therapeutic ratio, we had a trial that showed great promise in the setting of unresectable pancreatic cancer. And this was something that was investigator-initiated, was done at MD Anderson. Now it's at multiple centers. There's a phase 2 trial, multi-center, that we're going to really test this to see if there's a true survival advantage. So we're very excited about that. So again, this was the idea that starting from the patient, can we protect them from radiation injury to give them the proper dose that they need without compromising compromising the patient. And so we have many different ways to do this, and I'm agnostic until we find the best way. And maybe there are multiple ways. Maybe we can combine them. I don't know until we have something that works, multiple ways that work. I want to keep testing that. And then, pushing the limits with physics and radiation. There's a new technique called flash radiation. That's a whole nother talk. Working with Dr. Emil Schuler here on further improving the therapeutic ratio with new radiation techniques. So I want to thank our funding sources, my hardworking lab, and I want to take questions. So thank you all.
Thank you very much, Cullen. This was a wonderful lesson of translational medicine. Thank you very much. And now let's start the question. So first question. It's when you was looking at protective effect of fasting, did you look at differences in the female versus male mice?
That's a great question. So actually one thing that's known is that female sex actually can tolerate more radiation than the male sex. That's fairly well known, at least in mice. But we did not see any differences based on sex with fasting. But even so, accounting for that slight increase in tolerability of radiation in female sex, we did not see that.
Thank you. Another question. What is the mechanism of WR2721 only to protect normal tissue radioresistant and not the tumor?
Yeah, so basically the active compound protects from radiation wherever it is. So the actual mechanism is it's a prodrug that gets activated to the protective drug 1065 only in normal tissues. So it requires an enzyme called alkaline phosphatase to be fully activated. So that is the basis of it. So that is why we thought to use the natural digestive enzymes in the duodenum to activate this drug locally in the duodenum right where we need it. And what I didn't show you is that once it gets activated, the 1065 also kind of gets degraded fairly quickly. So that's why we think that approach is promising. But so that you have to be very careful with the route of administration with 2721, or emifosting.
Thank you. Another question. Would be possible to envision encapsulating the protective drug and targeting it to other locations, so making the application broader?
Oh yeah, that's what we're doing right now. I think that's what this company that's licensing this technology from us, that's something that they're trying to do, and I think it makes a lot of sense to do that. So you can imagine many different ways to do that, and where this becomes a problem of bioengineering rather than true biology. I think that, especially with amifostine, we've shown it's a great radioprotector. It's just a matter of getting it to stay in one place. That being said, there's been dozens of clinical trials that have shown that amifostine doesn't really get activated in the tumors. It has never shown protection of tumors. I've looked for it as well. I've not seen it. I've given it, but I think that's something you can never really shake. And I think that this method of using chemistry and engineering to limit the protective drug to a certain part of the body is a really great idea. Yeah.
Thank you. The next question. Did you check the level of nitric oxide in your radiation-treated cells or mice?
No, I didn't. No, we didn't. I think that's also something that has been purported to play a role. It's just not something that we knew how to do easily. So if you want to contact me offline after this, I'm happy to chat about that.
Great. And one more question.
Sure.
Cullen, did you ever check to this side of the genome who contain repeat elements? 50% of our genome is full of repeats, who theoretically should be silent. They should not jump from one place to another. Did you check in all these radiation type of therapeutics if this side of the genome, which is half of the genome quite, start or don't start having jumping elements between different loci?
No, that's a great idea. I think, in terms of, I don't know if that's ever been looked at, but I think that if, you know how to do it, I mean, we could easily radiate tumors. We could do it or cell lines in a dose-dependent fashion and actually assay for that. I think that would be a really interesting question. I mean, something we do see is, there are radiation-induced tumors. These usually happen 5 years, usually longer, 10 to 15 years after the initial radiation dose. In the radiation field, it's a different kind of cancer. And it's something we see in about 5 to 10% of patients who we cure initially. But on the whole, radiation is thought to be a fairly poor mutagen because basically the cells die before they get mutated. At least that's the thought, and that's the teaching. I mean, if you compare it, like say on an Ames test, compared to even peanut butter is a better mutagen than radiation in terms of inducing mutations. But to your question, George, I would love to look at that. I think it's such a simple idea too, and positive or negative, it's of great interest.
Thank you. So again, thank you, Cullen, for your talk. It was a wonderful talk. So all of you who attended, thank you. And please send emails to Dr. Taniguchi with all your questions. And I want especially to thanks to Cullen, but also to thanks to you who are here in numbers, very high, hundreds of people each talk, because without you, such webinars cannot be done. And of course, I want to tell you that we continue next Wednesday with another wonderful talk by Dr. Stephen Lay. So basically we continue till the end of May to keep this Enjoy Science running. And again, thank you, Cullen. It was a wonderful talk, and good best luck to all of you, and see you next Wednesday. Enjoy science and enjoy life. Thank you again, Cullen. Thank you to all.
Thanks for the invitation. Have a good rest of the day.